Hello everyone, in this video we will cover the section 3.2. In this section we will see properties of determinants. So firstly we will see the theorem 3. In this theorem we will investigate how to change the value of the determinant when we apply row operations for a given square matrix. Let A be a square matrix n by n matrix, or general form, if you remember, is given as Aij n by n. Okay, so if a multiple of one row of the matrix A is added to another row to produce a matrix B, another matrix, then the determinant does not change. We have the same determinant for the new matrix. So the first part of the theorem 3 says that if we apply replacement for a matrix, so you will get the same determinant for the new matrix. And we know when we apply row operations, they are row equivalent. They show the same properties theoretically. Namely, we have a matrix A, and in matrix notation it is given, for example, we write entries of the matrix for each row, and we do a row operation which is replacement. For example, R2, the second row, is replaced by R2 plus a number times R1. We use the row operation called replacement, and we obtain a matrix which is row equivalent to the previous one, and this is called in the theorem the matrix B. And when we look at the determinants of them, we see the determinant of the matrix A, is equal to the determinant of the matrix B. Okay, when we apply replacement, the first row operation, replacement, which is corresponding to the first part, we have the same determinants, namely this operation. If two rows of A are interchanged to produce B, then the determinant of the new matrix, this one, will be equal to minus determinant A. If we interchange the rows R2 and R1, okay, the second row operation, so the determinant of the new matrix B will be negative determinant A. Negative determinant A. This is very important. When we apply the second row operation, interchange, so the determinant is changing. Okay, we have negative determinant of the previous matrix. If one row of the matrix A is multiplied by k to produce B, then the determinant of the new matrix will be k times the determinant of the previous matrix. You know, this is called scaling. This is the third row operation. When we apply third row operation, namely R2 is replaced by k times R2, scaling, and the determinant of this matrix will be k times the determinant of the given matrix. Okay, determinant of the new matrix will be k times the determinant of new matrix. Namely, in this theorem we understand that if we apply replacement, so we have the same determinant. If we apply interchange, so the determinant will change, namely will be negative the determinant of the previous one. If we apply scaling, namely if we multiply a row by a number k, So the determinant of new matrix will be key times the determinant of the previous one. Okay. And we use row operations for finding the determinant of a matrix easily. Okay. For example, compute the determinant of the matrix A, where A is given here. So the strategy is to reduce A to echelon form and then to use the fact that the determinant of a triangular matrix is the product of the diagonal entries. If you find the the echelon form or echelon form of this matrix, so the computation will be very easy. Or our aim is to obtain a lot of zeros in a row or column. You know, we can expand this matrix according to any row or any column when we find its determinant. Okay, first we can find pivot position to obtain a lot of zeros for a row or a column. If we choose the first pivot position, which is 1, we can choose any number written here, any entry. 1 is very easy, we can multiply or we can add easily by using the number 1. We can apply easily the row operations. And if we get 0 for -2 and -1, so we obtain zeros in the first column and easily we can find the determinant of this matrix. So how can we obtain 0 for -2 and -1? Of course, we will do row operation. So to get 0 for -2, the matrix A is row equivalent. After the row operations, R2 is replaced by R2 plus 2R1, and R3 is replaced by R3 plus R1. And according to the theorem, we apply the replacement, which is the first part of this theorem. We have the same determinant. Okay, we can use the new matrix to find the determinant of the matrix A. So from here we obtain 1 minus 4, 2, 0, 2R1, 0, 2R1 minus 5, R3 plus R1, 0, 3, 2. R3 plus R1, yes, 2. 0, 3, R3 plus R1, R3 plus R1, 3, 2. This is true, I guess. So, as you can see in the first column, we have now a lot of zeros. Namely, we can find easily the determinant. So, the determinant A, according to the theorem 3 that we have seen in the first slide, this one, is the determinant of this matrix. This is called B in the theorem. It is equal to determinant B, and this is equal to we have zeros for entries except 1, therefore we don't need to write the terms corresponding to these entries, which are 0. So we are interested in just the number 1. So 1 times minus 1 to the power 1 plus 1, since it is in the first row and in the first column, times, by cancelling the first row and first column, the remaining numbers will form 2 by 2 determinant according to the formula. And from here we have 1 times plus 15, so we have 15. We have 15. Okay. We use the row operations for a given square matrix to find easily its determinant. 15. Okay. Another example. The matrix A is given by 2, 3, minus 3, 1, minus 8, minus 9, 0, minus 4, 6, 5, 1, 0, 8, 10, minus 2, 6. We have 4 by 4 matrix, and our aim is to find the determinant of this matrix. What is the determinant? Okay, so when we look at the matrix clearly, closely, so we have here the number 1, but it is in the 4th row, and we want to obtain the number 1 in the 1st row to make easier the calculation. Therefore, we do the row operation, which is the interchange. Okay, so the matrix A, our aim here is to obtain the echelon form of the matrix A, or we want to obtain a lot of zeros to make easier the calculation of the determinant. So A is row equivalent. We apply interchange, namely R4 and R1 are interchanged. So we get minus because of the theorem. If you know, this is the second part of this theorem, theorem 3. 1 minus 4, 0, 6, 3, minus 9, 5, 10, minus 3, 0, 1, minus 2, 2, minus 8, 6, 8. Okay. And from here we do the row operations, which are replacements to obtain 0 for 3, minus 3 and 2. We have 1. So R2 is replaced by R2 minus 3 R1, 3 R1. R3 is replaced by R3 plus 3 R1, row 1. R4 is replaced by R4 minus 2 R1, 2 R1. So we have minus 1 minus 4, 0, 6, and R2 is replaced by R2 minus 3 R1. So we have 0, minus 3 plus 12 minus 9 becomes 3, 5, minus 18 plus 10 becomes minus 8, minus 8. For R3 we have 0, 3 R1 minus 12, minus 12, 1 plus 18 minus 2 becomes 16, and the last row becomes 0, plus 8 minus 8, 0, 6, and minus 12 plus 8 becomes minus 4. Okay. So now we use the cofactor expansion to compute the determinant, and we use the first column since we have a lot of zeros here. Okay. So the determinant of the matrix A is equal to minus the determinant of this matrix, and using the first column easily we can write 1 times minus 1 to the power 1 plus 1, and we cancel the first column and first row, so the remaining numbers will form 3 by 3 determinant. 5 minus 8 minus 12 1 16 0 6 minus 4 and we don't write the other terms since we have 0 for the entries, which means that the multiplication will be always 0. We don't need to write the other terms in the expansion, cofactor expansion across the first column according to the first column. And from here we have minus, and for this one again we can obtain we can find a pivot position, and we can obtain a lot of zeros, but we have 0 already in the third row, and we can find the determinant of this matrix according to the third row. Let's use directly the formula since we have 3 by 3 determinant. According to the third row, the first term is 0 since we have 0 for the first entry. Therefore, we start with the second entry, minus 6 times minus 1 to the power according to the formula. It is in the third row and second column, times by cancelling the third row and the second column, the remaining numbers 3 minus 8 minus 12 plus 16, I guess, plus minus 4 the third entry times minus 1 to the power 3 plus 3 since it is in the third row and third column, and by cancelling the third row and third column the remaining numbers are 3 5 minus 12 1. Okay, so we have from here minus minus 6 times 48 minus 96, I guess, minus 4 times the determinant of 2 by 2 matrix written here, 12 minus 12 1, so we have 3 minus becomes plus 6t, and from here it is equal to I guess minus 36. Okay, using the row operations we can make easier the calculation of the determinant of a matrix like this one. When we apply the row operations we should be careful by looking at the theorem 3. Okay, this one. Okay, we should do the rules written here. Another theorem, a square matrix A is invertible if and only if its determinant is not equal to 0. Namely, we can know directly whether a matrix A is invertible or not by computing its determinant. If the determinant is not equal to 0, so we say it is invertible, which is very useful information. Just by finding the determinant we can obtain the information about the matrix A is invertible or not. For example, compute the determinant for this one. We have 4 by 4 matrix, and if the determinant is not equal to 0, so we understand that it is not invertible. Okay. So when we look at the first row, first column, -5 is not good for the number 3, and we have 0 here. Also we can use the fourth row since we have 0 in the third entry, as you can see. But -5 is not a multiple of -8 and 9. Also they are not multiple of each other. Therefore I think we are interested in 3 and -6. So we to get 0 for -6, we apply the row operation, which is the first one. R3 is replaced by R3 plus 2R1. So we obtain 3 minus 1, 2, -5, 0, 5, -3, -3, -6, and the third row becomes 0, -2 plus 7 becomes 5, 4 minus 7 becomes -3, -10 plus 4 becomes -6, -5, -8, 0, 9. Okay. We have the same rows. The second row and the third row are same, which means that the determinant is 0 because it is row equivalent if we do the row operations. Namely, R3 is replaced by R3 minus R2. So it is row equivalent. Let's continue from here. 3 minus 1, 2 minus 5, 0, 5, minus 3, minus 6, 0, 0, 0, 0, minus 5, minus 8, 0, 9. So it's determinant A. Since we do the row operation, which is replacement, we have the same determinants for this matrix and the given matrix in the example. So the determinant is equal to 0 because we have the 0 row here. All entries are equal to 0, and according to the formula, you know, we write the entries in the multiplication for each term, which means that the determinant is equal to 0, which means that the given matrix A is not invertible. A is not invertible. And another theorem, if A is n by n matrix, then the determinant of the transpose of the matrix A is equal to the determinant of the matrix A. Namely, we have the same determinants for the transpose and itself. Okay, I will not give the proof. And another important theorem, if A and B are n by n matrices, then the determinant of the product of them will be equal to the determinant of A times the determinant of B, namely the determinant of the matrix, the multiplication of them, is equal to the determinant of A times the determinant of B. This is very important information. Without finding the multiplication of them, easily we can find the determinant of the product of two matrices just by multiplying the determinants of them. Okay. Verify this theorem for the given matrices here, 2 by 2 matrices. First, we find the product of them. You can find yourselves. For example, for the first entry, we use the first row of the first one and the first column of the second one. The multiplication of the numbers respectively becomes 24 plus 1, and we obtain the first entry, and so on. You can find yourselves, and the determinant of the product will be 25 times 13 minus 20 times 14 becomes 45. And separately, the determinant of A is 9, as you can see. 12 minus 3 becomes 9, and the second one is 8 minus 3 is 5, and the product of them is 45, as you can see. Okay. And another example. The matrix A is given by 3 0 0 0 0 minus 7 2 0 0 0 8 minus 5 1 2 0 9 7 5 4 minus 2 minus 6 3 0 minus 1 0. Okay. Find the determinant of this matrix. So as you can see easily, the most useful row or column will have a lot of zeros. So when we look at the first column, you see except the number 3, all of them are equal to 0. Or you can use the last row. We have a single non-zero number, which is minus 2. This is 0, minus 2. You can use any of them to find the determinant. I think we can use the first column. According to the first column, the non-zero number is 3 there, which means that we don't need to write the terms corresponding to the entries which are zeros. So the determinant of the matrix A is equal to 3 times, by cancelling the first column and first row, the remaining numbers 2 minus 5 7 3 0 0 0 1 2 0 7 5 5 4 minus 2 0 minus 1 0. And when we look at this matrix, similarly we have a single non-zero number in the first column, therefore it becomes 3 times 2, and by cancelling the first column and first row we obtain this one, and directly let's find the determinant of this 3 by 3 matrix using the third row, since we have a single number, non-zero number, minus 2, so it becomes minus 2. It is in the third row and second column, times, by cancelling the third row and second column, the remaining numbers are 1, 0, 2, minus 1. So we have plus 2 from here, 12 times minus 1, which is the determinant of this one, becomes minus 12. Okay. And do we have another example? The matrix A is given in this form: 0, 2, 0, minus 2, 1, 5, 3, minus 5, 2, minus 7, 6, 4, minus 1, 3, 2, minus 2. Okay, determine whether the matrix A, which is 4 by 4, is invertible or not. Okay. So to learn whether it is invertible or not, let's find its determinant. Okay. When we look at the matrix, I think the first column again is useful since we have a lot of zeros, more than the others. Therefore, we will use the first column to find the determinant, and we can obtain 0 also for minus 2 by applying the row operation. So R4 is replaced by R4 plus R2, okay, to get 0 for minus 2. Using the second row, we have 2 here. So we have 0, 1, 2, minus 1, 2, 5, minus 7, 3, 0, 3, 6, 2, 0, R4 plus R2. So we have 0 again, minus 3, and 1. And now the determinant A is equal to, using the first column, 2 times minus 1 to the power, since it is in the second row we write 2, plus in the first column 1. And by cancelling the first column and second row, we obtain 1, 2, minus 1, 3, 6, 2, 0, minus 3, 1. And using the third row, it becomes so minus 2 times, we don't need to write the term corresponding to the first entry since we have 0, so we write directly minus 3 times minus 1 to the power 3 plus 2, since it is in the third row and the second column, and remaining numbers are 1, minus 1, 3, 2, by cancelling the third row and second column, plus 1, which is the third entry, minus 1 to the power 3 plus 3 times, by cancelling the third row and the third column, we obtain 1, 2, 3, 6, and we have minus 2 times the second term becomes 3 times 2 plus 3 becomes 5, plus 1 times 6 minus 6 becomes 0, so we have minus 30 from here, which means that it is not equal to 0. Determinant is not equal to 0. So because of the theorem, A is invertible. Okay. So using the theorem 6. Thank you very much for your listening.